All right, time for our final kinematic equation. Again, this one's going to be a little more complicated in how we use it. This one is also going to be a little more complicated in how we derive it. What we do is we start with the basic acceleration equation. A equals delta V over delta T. Change in velocity over change in time. And what we're going to do is rearrange this equation to solve for delta T. So to do that, we multiply both sides by delta T to get it out of the denominator. So that gives us delta T times A equals delta V. And then divide both sides by A to isolate our variable. So change in time, equals delta V over A. That's the first step. Taking the basic acceleration equation and solving it for change in time or delta T. The next thing we want to do is substitute the equation for delta V in the place of delta V. So delta T equals VF minus VI, the equation for delta V, over A. That is, again, just rearranging the basic acceleration equation and then replacing delta V with its expression, VF minus VI. Now we're going to go back to one of the early kinematic equations that I taught you. Delta X displacement equals 1/2 VF plus VI times delta T. I think that was the first one that I taught you. And what we're going to do is we're going to place delta T with this expression here. We're going to take delta T out and we're going to put VF minus VI over A in its place. Now I'm going to rewrite this a little bit differently. Instead of having 1/2 times this, I'm going to put VF plus VI over 2, same thing, times that equation, VF minus VI over A. And all that equation is taking the very first kinematic equation I taught you and replacing delta T with what delta T equals from the acceleration equation. Delta T is equal to VF minus VI over A. So I just took this out and replaced it with that. Now, if we multiply this through, we get delta X equals VF squared, VF times VF, minus VI squared, positive VI times negative VI, over 2A. And again, we could just leave it at this if we wanted to. We could do plenty of math with that, plenty of calculations with that, and get the exact same answers. But if we want this to look like the standard form for this kinematic equation, what we have to do finally is solve for VF squared. So first thing I would do is multiply both sides by 2A. So 2A times delta X is equal to VF squared minus VI squared. And then I'm going to add VI squared to both sides. That all cancels out. Writing it in a standard way with our single variable over on the left, VF squared equals that. VI squared plus 2A times delta X. That's it. That is our fourth and final kinematic equation. Now, the thing about this one that is, again, going to be the tricky part are the squared things. And it's tricky for a couple of reasons. First, students forget that the VF and the VI are squared. So whenever they're solving for VF or VI in problems, they forget that they have to square root everything at the end to change VF squared into VF or VI squared into VF or VI. It happens all the time. The second thing is that whole unit cancellation stuff, making sure that the units cancel out. We've got squared units on our velocities. They're going to need some squared units on our accelerations again. So we can't really use mile per hour per second. None of those real long acceleration units again. It's going to have to be something like miles per hour squared or meters per second squared or feet per second squared or whatever. It's going to have that time squared unit for A. And again, make sure everything matches up just like it was in the previous kinematic equation. It's a very similar idea, very similar concept, plus the added twist of sometimes solving for squared variables. VF squared equals VI squared plus 2A times delta X. And again, all the parentheses means it's times. So a car travels at a velocity of 20 meters per second squared. If the car decelerates at a rate of 3.1 meters per second squared, that's just seconds up there. Do that. To a final velocity of 7 meters per second. How far will it travel? Mix it up a little bit this time and do a little algebra right out of the gate. So, same old problem solving process. Figure out what the numbers are. It's traveling at a velocity of 20 meters per second. So we know that's a velocity. And it's going to be initial. The reason why I know it's going to be initial is because down here it says final velocity of. 3.1 meters per second squared is an acceleration. And it is decelerates, so that's negative. Deceleration means slowing down. Slowing down is negative acceleration. And it hits a final velocity of 7 meters per second. Those are all the numbers we have. Again, we can think about hidden numbers. We have both velocities here, so there wouldn't be anything coming to a stop or at rest. There wouldn't be a third velocity, so we don't have any of that to consider. And we already have an acceleration, so we're probably not dealing with a falling object or an object thrown up in the air. And if we look at the question, there's none of that there either. So no hidden numbers. Identify what we're trying to find. We're trying to find how far, and that is delta x. Now, just like the previous kinematic equation, we've got to make sure that all of our times and distances are the same. And we look here, all of our times are in seconds. That's great. And all of our distances are in meters. That's great too. Nothing to convert. All of our units are the way that we need them to be. So we can go ahead and start substituting into this equation to solve it. Again, remember, at this point, we know that's the equation we're going to use because we're just doing a single equation at a time. Remember, when we get to the mixed sets next, you will look at these four things and you'll pick the equation that has those four things in it as the one that you're going to use. So VF is 7 meters per second. That is squared. That is equal to VI, which is 20 meters per second. Plus 2 times A, which is 3.1 meters per second squared. Times delta X, my variable. Now we need to do some simplification here before we do anything else. So the first thing I'm going to do is take care of these squared numbers. 7 squared is 49. That would be meters squared over seconds squared. I end up squaring them both. I'll do 20 squared. 20 squared is 400. Again, it would be meters squared over seconds squared. Then I'll do 2 times 3.1. Simplify that, that's 6.2. That doesn't do anything to the units in this one. Times delta X. Since the 2 doesn't have any units on it, that doesn't do anything to change those units. I will begin by subtracting 400 from both sides. So 49 minus 400 is negative 351. A negative sign there. That's negative 3.1. I was looking at the negatives thinking, what's going on with that? That's negative. That's still meters squared per second squared. And that's equal to this, negative 6.2 meters per second squared times delta X. And then to solve, I'll divide both sides by negative 6.2 meters per second squared. So that all cancels out. And it's delta X equals. The second squared will cancel, and one of the meters will cancel because it's meters squared over meters. So my final unit will be meters on my answer. That's all that's left. 351 divided by 6.2 is 56.61290. And we're not using significant figures. So we'll call it 56.6. And again, the only unit left would be meters. Again, a lot of this is about unit cancellation, just like it was before. We want to make sure that when we get into the end here, all of our times cancel. One of our distances cancel in this case, leaving us with a good unit for our answer. And the only way that's going to happen is if all these distance units are the same, and these are all meters, and all these time units are the same, and they're all seconds. If they're not all the same, then we have to convert, make them the same, or the units will not cancel correctly. All right, let's do another one with a little bit more work involved with it. So a car accelerates at a rate of 1.7 miles per hour per second. To reach a final velocity of 57 miles per hour. car covers a distance of, let's say, 375 feet. What was the initial velocity of the car? All right, normal problem-solving process. Got to figure out what everything is. Accelerates at that. Let's say final velocity of, that's VF, covers a distance of 375 feet. That's delta x. And again, we're using distance and displacement as the same thing here because this is just linear motion. And hopefully, I've chosen my random number as well. And we're moving in a single direction here. We're trying to find the initial velocity. No hidden numbers in this one. Doesn't say anything about from a stop or at rest. So we can't assume VI is 0. We got to figure out what the VI actually is. And we already have an acceleration. So odds of us having to deal with free fall are slim to none. Now let's look at the units. Got a couple of problems. Miles, miles, feet. That's no good. Everything has to be the same. So I'm going to have to convert these feet into miles. 1 mile equals 5,280 feet. I start with the 375 feet times and then a fraction bar. Whatever unit I have here is the one I have to put on the bottom. So the 5,280 goes on the bottom. The 1 mile goes on top. Technically, it's 375 times 1 divided by 5,280. But the way I generally tell you to work with this is if that 5,280 is on the top, you would multiply by it. If it's on the bottom, you would divide by it. So it's on the bottom this time. So it's 375 divided by 5,280, which is 0.07102272727, repeating. So I'm just going to do 0.071. And that would be miles, because that's all that's left. And again, coming into this class from honors chemistry and having taken algebra 1, many of you haven't taken physical science, it's expected that you can do this dimensional analysis to do the conversions. You might not know the equivalents. I'll provide those. Just make sure that you can do those conversions. That's an expected skill, prior knowledge that you have coming into this class. The other issue I have here is this is seconds and that is hours. So I can either convert this into miles per hour squared, or I can convert this into miles per second. Let's do something different this time. Let's convert the 57 miles per hour into miles per second. So if I go 57 miles in an hour, if I divide that by 60.95, that's how many miles I would go in a minute. And then if I divide that by 60 again, that's how many miles I would travel in a second. It was basically 57 divided by 3,600, the amount of seconds in an hour. 0.01583 repeating. And that will give me miles per second. And that should do it. That should hopefully work. If not, well, we'll find out. All right. Now, just for fun, just to make sure everything works, let's talk about how you would convert 1.7 miles per hour into miles per second squared. What we end up having to do is convert the miles per hour, the 1.7, into miles per second, just like we did before. So if you travel 1.7 miles in an hour, divide that by 60.0283 repeating, that would be how many miles per minute you would go in a second. Divide it by 60 again. That would tell you what your acceleration is in miles per second. That is 4.72 repeating times 10 to the negative 4 miles per second squared. It's a really small number because you're talking about how many miles you travel in a second, which is going to be a really small number anyways. But that's a surefire way to make sure everything works unit-wise. All my distances are in miles. All my times are in seconds. If I want to make things nice and complicated and complex for you, this is what I do. So VF squared, that's this number. That's miles per second. That is squared. Equals VI squared plus 2 times A, which is that number. Miles per second squared times 0.071 miles. Another there. So again, I'm going to do a bunch of simplification. I'm going to go ahead and square that. 0.0158 squared, 2.4964 times 10 to the negative 4. That'd be miles squared over second squared. That's equal to VI squared plus. Or on this side, it would be 2 times 4.7 times 10 to the negative 4. Make sure you know how to use your exponential notation functions on your calculator. Times 0.071. That's 6.674 times 10 to the negative 5. It's miles times miles, so that's miles squared over seconds squared. Now I'm going to subtract 6.674 times 10 to the negative 5 from both sides. So 2.4964 times 10 to the negative 4 minus 6.674 times 10 to the negative 5. Do all that. Parentheses keys 2.4964 10 to the negative 4 minus 6.674 times 10 to the negative 5. I punched it wrong. Minus 6.674 times 10 to the negative 5th. I don't know why it doesn't want to do that for me. I get 1.829 times 10 to the negative 4. And this would be miles squared over second squared. And that is equal to VI squared. And then we have to remember at this point that we have to take the square root of both sides. so that it's VI equals. That's 0.01352. I was around 0.14 because this is in the way. Because we square root of this, it's just going to be miles over seconds. Very small number because that is a little strange of a unit, miles in every second. We want to convert that to miles per hour. We would take that times 60, and that would be miles per minute. Times 60 again, it would be miles per hour. It was 48.7 miles per hour. And again, just doing this unit stuff and getting some weird units here to work with, because I got to make sure that all my units work out the way I need them to. When I'm done with all this, I need to make sure that this is the same as this, because I'm going to be subtracting. So miles squared per second squared is what I have over here. So I have to make sure this is miles squared per second squared over here. Which means I did have to convert that into miles per second squared. So that wasn't just a wasted extra step. That had to be done. If I had left this as miles per hour per second for my acceleration, I would have miles per hour per second over here times miles. So it'd be miles squared times hours over seconds. And when I went to do the subtraction, that wouldn't work. So yeah, that wasn't just a wasted step there. Thinking ahead and just going ahead and doing that conversion was the right thing to do. So making sure that all my distance units are the same, all my time units are the same, that's necessary. That's a vital function in making sure that this works. Sounds like I can make this good and challenging. So be prepared. I mean, it's honors physics.